Um, we're going to be working with exponential functions and finding their domain and range. So we've worked with exponential functions before, and that you know that this equation right here, it would look like y equals 1 times 4 raised to the x power. So that 1 is going to be your y-intercept. The constant multiplier will be the number that's raised to the power, which would be 4. And since that 4 is more than 1 or greater, then it's going to be a growth. And the asymptote is where it levels out. So if we were going to put this equation in the calculator, we know that the y-intercept is 1. So it's going to go hit that, and then it's going to increase. It's a growth. So that's what it's going to look like. So therefore, where it levels out, right here, it goes through the y-axis, and it levels out at 0. So therefore, your asymptote is y equals 0. Not x equals 0, it's y equals 0. All right, problem 2. Your y-intercept will be 8. Your constant multiplier is 1.2. So therefore, this is also a growth. So if the y-intercept is 8, so 1, 2, 3, 4, 5, 6, 7, 8. We know it's going to go through there. And therefore, it's going to look kind of like that. And you can put it in the calculator if you want, just to look at it. But that's what it's going to look like. And again, the asymptote, it's never ever going to hit 0. It's going to keep getting closer and closer to the 0, but it's never ever going to hit. So this is where it's leveling out. So therefore, your asymptote, remember the P is silent, asymptote would be 0. All right, over here, we've got a y-intercept of, if you look at it and graph it, it's going to have a y-intercept of 4. Let me make sure I have the right color. It's going to have a y-intercept of 4, because remember, it would look like y equals 1 times 1/2 raised to the x plus 3. So you have the 1, and then you add plus 3, and that gives you the 4 for your y-intercept. But you could just look at the graph. At this point, we're just more concerned that you understand and can read the graph. The constant multiplier is 1/2. So since that is less than 1, this one is going to be a decay. So if the y-intercept is 1, 2, 3, 4, it's actually going to look like this. Okay, and so it's going to level out right here at when y is equal to 3. All right, now then. So that's just a little review on what different things of identifying the exponential functions on a graph. Now then, we're going to look at their domain and ranges. So it says for any general exponential function, the domain will be all real numbers, and the range will be mostly greater than the value of the asymptote line. Sometimes it will be less than. So if you look at example 1, y is equal to 3 raised to the x power. So the domain, see, the big thing is that you have the arrows here. So there's never going to be a starting point or an ending point. So it's all numbers. Your range, just like they said, most of the time will be greater than the value of the asymptote. So the asymptote is where it levels out, which in this situation is going to be y is equal to 0. So you would read this as y, that vertical line means such that. Y such that all y values are greater than 0. Okay, number 2, again, you have arrows here. So there's never going to be a starting or an ending point. So that your domain is all real numbers. And again, this levels out at 0. So that would be, your range would be y is greater than 0. Number 3, again, you have arrows on the ends. So it's going to be all real numbers. And this time it levels out at -1. So when y is equal to -1, therefore, your range would be all number y values that are greater than -1. All right, let's see what we can do by ourselves here. So on this one, for your domain, you have an arrow here, an arrow here. So it's going to be all real numbers. So if you just want to put ARN for abbreviation, you are welcome to do that. And then your range would be the asymptote. So we have to identify the asymptote, which would be y is equal to 0. So therefore, it would be all y values such that y is greater than 0. All right, let's take a look at number 5. So again, we have arrows here. So your domain will be all real numbers. Your range, here is your asymptote at y equals 0, but it's a decay. It's going down. So instead of it being greater, it is going to be less than. So it'll be all y values such that y is less than 0. Never equal to, though. Remember, it's never ever going to hit 0. It's going to approach 0 and get really close to it, but it's never ever going to hit. All right, let's look at number 6. For the x values, well, there is a starting point. So when you draw a line through the x-axis, it hits the origin at 0, but then there is an arrow, so it'd be greater than or equal to 0. And then your y is right here. So if that's 0 and go to 60, halfway would be 30. So, and again, you have the arrow. So it'd be y values such that all y values are greater than or equal to 30. All right, let's look at number 7. See if we can write down our domain. You have arrows. So we're going to actually have you write the braces. I know some of you struggle with that. We're going to put all real numbers. Here's your brace. So it just looks like that. All real numbers. Your range value. Okay, so here's your asymptote. I already have it drawn. So that's y is equal to 2. So we're going to have all y values such that y is greater than, but not equal to. Don't put, it's never ever going to hit that whole number 2. So y is greater than 2. All right, let's look at number 8. So our x would be 0 to 20. So that one's pretty easy. So this is the old school, okay, where you have endpoints, no arrows. The range, okay, so let's deal with the range. The lowest part of it is 1,000. The highest part up here is going to be halfway, a little more half. Oh, those go by 2s. So 42, 44, 4,600. There we go. All right, so let's see if we can answer some of these questions. So on the problem situation, the table shows the number of players remaining in a tennis tournament where the losing player is eliminated after each game. The function f of x equals 32 times 1/2 raised to the x power describes the table. What is the range of the function? So the range, remember, is the y value. So that would be these right here, and we're going to write it in order from least to greatest. Now, these are individual points, okay? So it's not considered continuous. This would be a discrete function. So you list the individual points. Okay? So we would have 1, 2, 4, 8, 16, and 32. So there you go. All right, let's look at problem 10. Henry invested $2,000 in a bank account that earns 1.2% interest compounded annually. He plans to leave his money in the bank no longer than 10 years. Then will withdraw all of it at the same time. All of it at that time. What is a reasonable domain for this situation? Now then, anytime you're dealing with money and you're dealing with time, well, not necessarily money, but you're dealing with time for the domain. Okay. He plans to leave money no longer than 10 years. So you're talking about 1 year, 2 year, 3 year, not like, 1 and 2/3 of a year. I mean, it goes by years. So therefore, this is going to be a discrete function. So your answer would be letter C. I believe that's all the notes. It is. All right. Signing off.